right, we're going to go ahead and dig into function transformations mathematically here so we can see what it is that these transformations actually do. And so I want to start by introducing the function that we have on the screen here. So up at the top we've got the function graphed, and its definition is cosine of 2x plus 0.5x, and it's not that important what this actually is. What is important is that this graph is not symmetrical, it's changing, and the reason that I selected this function is because of those things. We're going to be able to see changes in the shape a lot easier than we might if we were working with something like a parabola. Now, transformation of a function, as we've seen, is a way to change the shape so that we can stretch, shift, reflect the function to change it from its basic form, maybe its parent form, into something useful that matches perhaps an application that we have in mind. We have four different parameters, four different numbers that are going to be involved in transforming a function. The first one is called a, the second is b, then we have h, and we have k. And where those things live in the function is indicated by this general model right here. And so I'm going to walk through this real quick and just show you kind of which function or which parameters are where and what effect they have on the function as we transform it. The first value here in orange, this a, multiplies this whole piece right here. And so if you look at this piece right here, this is basically my f of x. In fact, when b is equal to 1 and h is equal to 0, as I showed down here, b is 1, h is 0. So 1 times this stuff is not going to change it, and x minus 0 is not going to change x. And therefore, this piece right here is just f of x. This is just my y value. So a is a number that's multiplying the y value. K is a number that's adding to the y value. In this case, k is 0, so that doesn't change the y value when I add. And a is equal to 1, which does not change the y value when I multiply. So right now with a equals 1, k equals 0, this is just f of x. And so you can see on here the black curve is going to be my original f of x, and the green dotted curve will be my transformed function. And right now you can see that they're the same. Let's change a, and I'm going to just set this to kind of a friendly number, a equals 2. So what effect is this going to have? Well, nothing else has changed here, so this is still f of x. This is still my y value. All I'm doing now is multiplying my y values by 2. And so if I pick a y value, let's say this y value right here, okay, it's got an x value that's close to 0 right down here somewhere. But the point is that if I take this y value of 1 and multiply it by 2, I get a y value of 2. And so my transform function has a y value of 2 at this point. Over here, I've got a y value that seems to be a little bit higher than 2.5. Okay? At the same x value, where my y value of the function was about 2.5 or so, if I multiply that by 2, I should get a y value that's a little bit more than 5. And let's look at y value that's negative. If I go over to this one, for example, I can see that that y value is a little bit less than negative 3. And if I multiply that by 2, I should get something that's a little bit below negative 6. And so basically the idea of a is that it has this effect of stretching in the vertical direction only the height of the curve. So when a is a number like 2, it's going to make the graph twice as tall. Notice that it does not change anything in the horizontal direction. It's just making it taller or shorter. So I'm going to go ahead and stretch it big. I'm going to come back and stretch it smaller. So notice now that I'm actually compressing this graph down from its original height towards the x-axis. And this occurs when a is less than 1. Matter of fact, if I set a equal to 0, what am I doing? I'm multiplying, come on, there we go. I'm multiplying all my y values by 0, and therefore my function has a whole bunch of y values that are 0, and that's it. I can see down here, 0 times my y value is going to give me 0. Now, if I change a in the negative direction, two things are really going to happen. Let's set it to negative 2. Not only am I doubling the size of the y value, but I'm changing its sign. So here where we had the y value of 1, okay, I'm doubling it to a y value of 2, but I also have this negative sign to deal with, which means that now I've reflected below the x-axis, and that is another function that A performs. Is when A is negative, it makes the graph a reflection, a vertical reflection over the x-axis. So watch as I change A from various values. Negative, we get a stretch and a reflection. A small negative number, we get a compression with a negative reflection. As I make A a little bit bigger, it's still compressed compared with the original graph, but it's in the same direction because it's positive. And now with A being a value greater than 1, my y values are greater in magnitude, and because it's positive, they're going in the same direction. So that's the job of A, vertical stretch and compression, okay, and also reflection depending on the sign of A. Okay, now we're going to go ahead and look at the effect of the parameter k. Now everything else has been set back to its neutral position, so A is 1 once again. So 1 times f of all of this is just f of x. This whole piece is f of x. So when I change the value of k from 0, I'm basically just adding some number to my y values. So let's go ahead and change k to a number like 2 and see what effect that has. Basically all that's done is taken every y value on the graph and added 2. Take a y value, add 2. Take a y value, add 2. Y value, add 2, and so on. And that really just has the effect of copying the graph 2 units up. In fact, you can see from this dotted line right here that the x-axis can be thought of as being shifted up as well. Now if I take k and make that negative, let's make it negative 2. Notice that I'm adding a negative number, which is really the same thing as subtracting. And so when I subtract a number from my function, I'm shifting the graph downward. So k's job is to shift the graph upward or downward. Okay, no other changes to the shape, just simply a change in position. This is also called translation, vertical translation. Okay, and then speaking of translation, we have another translation, this time horizontally, left and right. And we're going to translate or shift the graph by h units. And the way that we're going to do that is by subtracting this value of h from x before we plug it into the function. So right now everything is reset. A is 1, B is 1, h is 0, k is 0. Everything you see here is really just f of x. I'm going to go ahead and set h to a value of 2, and let's see what this does. So if you notice what's happened is h is set to 2. I've shifted my graph 2 units to the right. So let me go ahead and just kind of do that so you can see the graph itself shifting. Okay, I've shifted the graph 2 units to the right. Now, this says x minus 2, and this can be a little bit confusing because when you look at this and say, oh, this is negative 2, I must be shifting left. It's not negative 2 because the number we're looking at really is this. Notice that h is being subtracted from x, not negative h, okay? So if h is a positive number, x minus a positive number, well, it's just x minus that number. If I were to change h to negative 2, okay, I've shifted the graph 2 units to the left now. Notice that I have x minus negative 2, which really gives me x plus 2. So when I have x plus 2, that's really x minus negative 2 because h is negative 2. Okay, so this is one reason why things are sort of backwards inside here, because I'm actually subtracting this number here. I'm going to set this back to 2 here for a second. And I want to show you another way to think about this. Okay, this can be a little bit confusing, so try to follow along here, but it does help explain why we have this backward action here. Suppose that I want to plot a value of y here at x equals 2. And I have this transformed function. So I'm really trying to plot my green function. So I plug in x equals 2, but what this tells me to do is to actually take 2 away from the number I'm plugging in. In other words, move left by h units. So I'm going to go over h units, and I'm going to pick up My x value is now 0, 2 minus 2. I'm going to pick up my y value from here, but remember this y value is actually what I'm plotting right here. So I've basically said, okay, in order to plot my green function, I plug in 2, but my green function says subtract 2 first, get my y value, and bring it back over here. This is why the graph appears to be shifted to the right when I have a negative subtraction going on here. I don't want to say negative number because this is the number, this is a positive number, but x minus 2 means shift to the right for that reason. So h's job, basically, just to shift the graph left and right. The last transformation that we have here is our b value, and what b does is takes my x value that I'm plugging in, and possibly I've changed it with an h value here, but it's taking that value and then multiplying x by something before plugging it into f and before getting multiplied or added to my two parameters outside. So what effect does this have? Let's take a look. As b increases, let's go up to b equals 2, my graph actually gets narrower. Okay, so I've actually changed the shape, compressing it in a horizontal direction. And the larger the value of b gets, the narrower the graph gets, the more compressed it gets. Okay, now contrast that to b equals 1, where the graph is the same as what I started with. If I start using numbers less than 1 but greater than 0, I'm actually stretching the graph out. And when b is actually equal to 0, I just get a horizontal line at whatever my y-intercept is. And I'll talk about the reason for that in just a second. But notice then what happens as b becomes negative. The numbers get larger in the negative direction, my graph gets narrower, but it's reflected across the y-axis. So if I make b equal to negative 1, what we see is a reflection from any x value, let's say about, where's that peak at right here, about 3 1/4 more or less, okay? We're going to take that and we're going to end up with that same y value over here at negative 3 1/4. So we have to take our x value, okay, which is 3 more or less, and then we're going to plug it in and we're going to multiply it by negative 1, and that's going to give us negative 3. So when we want to plot the value here at 3, okay, on our green function, we're actually going to go over to negative 3 to get our value, which is our y value here, bring that back over and plot it at 3. And so for the same reason that I explained with h, this is why a bigger in magnitude value of b makes the graph smaller, and a smaller magnitude, okay, something less than 1, gives us a stretched graph, something that's wider. Okay, and then b equals 0 just completely flattens out the graph because I'm always plugging in 0, because no matter what my x value is and no matter what my h value is, b is 0. That makes everything here 0. So for all values of x, my output is really f of 0, which is my y-intercept. Okay, so let's just look at all of these all together. I've reset everything so that my transform function is the same as my original function. We have a stretch, vertical stretch with a. The bigger a gets, the more of a stretch it is. If a is between 0 and 1, we're actually compressing, okay, from the function towards the x-axis. And if a becomes negative, we're going to be reflecting across the y-axis. With b, kind of the same thing happens, except now we're going in the left and right, or the horizontal direction. We get a stretch of the graph when b is between 0 and 1 in magnitude. And when we change the sign of b, we change the reflection of the graph. When b is a large number greater than 1 in magnitude, we get a compression of the graph. So same effect as a, more or less, it's just that it's happening in the sort of opposite direction. H and K are our translations. So H simply moves the graph left and right. Positive values of H give us movement to the right. Negative values of H to the left. But notice that since we're subtracting in here, the action is actually opposite of what you might expect. This would probably be written as x plus 3.9. And finally we have K that shifts the graph up and down.